Okay, 2.50, we are given a moving delta function well with an argument of x minus vt, which represents a traveling wave, where v is the constant velocity of the well. In part A, we want to show that the time-dependent Schrodinger equation emits the following solution that we're given, this very complicated absolute value expression, with E being the energy being equivalent to negative m alpha squared divided by 2h bar squared as the bound state energy of the stationary delta function. So our hint is to plug it in to the Schrodinger equation as we've done in the previous problems, and then we want to use the result of 2.23b. So 2.23b gives us the step function. Theta of x is equal to positive 1 when x is greater than 0, and 0 when x is less than 0. So the result from 2.23b was that the derivative of this with respect to x, d theta by dx, was actually equal to the Dirac delta function, Dirac delta of x. So if the hint is telling us to use this result, evidently we're going to want to somehow convert this expression into a theta function, into a theta step function somehow, so that when we derive it with respect to x and plug it into the Schrodinger equation, we start getting Dirac delta functions. So our first goal, therefore, is going to be somehow to convert this given wave function here into the form of a step function. So really the only thing that has this sort of step behavior is going to be these absolute values in the psi expression. So what we can do is we can recognize that the magnitude or the absolute value of any function, not x minus vt, because that's a little bit too complicated right now. So let's start simple and look at the absolute value of just x. This equals a step function, or not a step function, but it equals a piecewise, where if x is greater than 0, then it just equals x. However, if x is negative, then it equals negative x, where x is less than 0, because and the logic for here is that this result always has to be positive. So if x itself is already positive, then nothing happens. However, if x is negative and we're taking the absolute value of it, the result has to be positive. So this actually equals the negative of x, where x itself is a negative, so the two negatives cancel out to make a positive. So this, in a way, is a piecewise that looks very similar to our step function. However, we're not quite there yet, because if we distribute out the x, then we get that this is equal to x times the piecewise of 1 when x is greater than 0, and negative 1 when x is less than 0. This is not quite what we want, because we see here that our step function equals 0 when x is negative. Here we have it equal to negative 1 when x is less than 0. So to get it like this, hopefully you've seen this before in an earlier problem. In fact, I know that this was shown in an earlier problem. I just don't remember which one. To get something like this, we have to take a linear combination of step functions. And to do that, I'm going to recognize that the step function theta of negative x is going to give me something very similar, where it equals 1 when negative x is greater than 0, and 0 when negative x is less than 0. And if we move these inequalities around, remember that moving a negative sign on the upper side will switch the sort of the sign of the greater than or less than. So this becomes when x is greater than and when x is less than 0, respectively. So this becomes when x is less than 0, and this becomes when x is greater than 0. So basically all that happens here is that the signs get inversed. And in that case, this is sort of exactly what we want, because what that implies is that we can rewrite this absolute value expression as x times theta of x, which is our step function, subtracted by theta of negative x. And what that's going to do for us is that this is going to give us sort of the exact piecewise that we want. Because remember, theta of x is going to be 1 when x is positive and 0 everywhere else. And then theta of negative x is going to be 1 when x is negative and 0 everywhere else. These two functions, when they add together, will produce this expression where it's going to equal 1 from the theta of x when x is positive, and negative 1 from theta of negative x when x is negative. And everywhere else they don't affect each other, because Everywhere where theta of x is non-zero, theta of negative x is going to be 0, and everywhere where theta of negative x is non-zero, theta of x is going to be 0. And this expression specifically actually has a nickname because of how common it shows up in higher level mathematics. It's called the signum function, SGNX. So in actuality, the absolute value of any expression can be expressed as that expression multiplied by the signum function of that expression. And from here, we can plug this in to the Schrodinger equation and actually start getting valid solutions. Okay, so now with the knowledge that the absolute value of any expression can be expressed as sort of that expression multiplied by signum function of that expression, we can take this wave function and start rewriting it in terms of this. So what we see here is that the only absolute value expression is this magnitude of x minus vt term. So magnitude x minus vt is going to turn into x minus vt, multiplied by the step function theta of x minus vt, subtracted by the step function of the negative of that, so vt minus x. So if we write out the wave function now, it's going to be psi of x comma t is equal to the square root of m alpha divided by h bar times the exponential e to the negative m alpha over h bar squared multiplied by x minus vt times, actually, it'd be better to move that out of the bracket. So multiplied by x minus vt multiplied by the signum function theta of x minus vt minus theta of vt minus x. And then we're adding this next exponential. So let's just combine everything together. So minus I over h bar multiplied by e plus 1/2 mv squared. Close this off, multiply it by time, minus mvx, and close off this bracket. And at this point, now we can start sort of taking derivatives. So let's do that next. Okay, so let's solve the derivatives. So start with the derivative of psi with respect to time. That's going to give us d psi by dt is going to equal, so the constants at the front remain unchanged, h bar, and then let's see. So this is going to be the exponential of everything I've written so far. Minus I over h bar, e plus 1/2 mv squared times t minus mvx. And then the derivative of this expression, so d by dt of negative m alpha over h bar squared, x minus vt, theta x minus vt minus theta vt minus x minus I over h bar e plus 1/2 mv squared times t minus mvx. And I'm going to look at this separately because this is such a long expression. I really don't want to rewrite this multiple times. So let's see. If I distribute this out, this is going to give me negative m alpha over h bar squared on the outside, multiplied by d by dt of x minus vt multiplied by piecewise theta x minus vt minus theta of vt minus x, and then subtracted by, so the derivative of this expression, this term at the back instantly cancels itself. So the derivative is just going to be minus I over h bar e plus 1/2 mv squared times t, which is just going to give the front. So this is going to be subtracted by I over h bar times e plus 1/2 mv squared. So this expression over here is a little bit annoying. Let's see. So I'm going to use product rule here. What's this going to give me? Box prime times triangle plus triangle prime times box. This is going to give me d by dt of x minus vt multiplied by our signum function. And then added with x minus vt times d by dt of our signum function. Okay. And then at this point, if I want to calculate the derivatives of this front expression is just going to evaluate very simply. So the x goes to nothing, and then over here we leave behind a negative v. So negative v times theta x minus vt minus theta vt minus x. And then over here we can apply chain rule once again to this expression. So let's see. What is this going to give us? If we use chain rule a second time, we're going to get plus x minus vt multiplied by derivative with respect to time. So yes, okay. So the derivative of any sort of Dirac of any step function is always going to give a Dirac delta, but because of the sort of function that's ingrained within this step function, we have to use product rule again and derive the interior by time and attach it as a multiplication factor at the front. So d by dt of x minus vt is just negative v. So this is going to be negative v times the derivative of the step function, which is going to be a Dirac delta function of x minus vt, as we've defined up above, subtracted by the derivative of vt minus x, which is positive v with respect to time. So minus v times the Dirac delta of x minus of vt minus x. My apologies. So then we take it back up here. And we realize that there's a common factor of negative v everywhere, so we can plug that back in and get rid of the negative at the front. So we're going to get m alpha v over h bar squared. And then, let's see, this is going to be multiplied by theta of x minus vt minus theta of vt minus x plus x minus vt times the Dirac delta of x minus vt minus the Dirac delta, or I suppose in this case it would be plus, I think, yeah, plus the Dirac delta of vt minus x. And then subtracted by I over h bar times e plus 1/2 mv squared. Okay, let's see. So at this point, we seem to be sort of stuck because there doesn't seem to be any way to sort of simplify this any further. So it seems like the resulting expression is just going to be this really disgusting looking mess. However, there is a sort of a hidden thing that we can do here, which is I can recognize that, you know, the Dirac delta function over here, there's nothing necessarily stopping me from inverting the argument and saying x minus vt instead. Because remember, a Dirac delta of any function x is going to equal either 1 when the argument is equal to 0, or sorry, my apologies. A Dirac delta is going to be infinity when the argument is equal to 0, or it's going to equal 0 when the argument doesn't equal to 0. So in reality, a Dirac delta of x minus vt is going to equal infinity when x equals vt and 0 when x doesn't equal vt, but it's also going to be the exact same piecewise of vt minus x, because this is also going to be infinity when x is equal to vt, and it's also going to equal 0 when x doesn't equal vt. So in reality, these two functions are the same. We can rewrite them in the exact same way, in which case our expression becomes m alpha v over h bar squared times theta of x minus vt minus theta of vt minus x plus 2x minus vt Dirac delta x minus vt. And then we're adding the negative I over h bar e plus 1/2 mv squared at the back. So at this point now, we can once again sort of take advantage of the math a little bit and recognize that sort of this 2x minus vt times Dirac delta x minus vt term is always just going to be 0, because in the case where x doesn't equal vt, the Dirac delta function is going to equal 0, and it's going to make everything in this expression 0. In the case where x is equal to vt, although the Dirac delta jumps up, the x minus vt term is now equal to 0, so that cancels out everything. So this expression, no matter what, is always equal to 0, and it doesn't matter, so we can just exclude it, which gives us a final derivative expression, m alpha v over h bar squared times theta of x minus vt minus theta of vt minus x. And this is going to be subtracted by I over h bar times e plus 1/2 mv squared. And at this point, we might as well also sort of rewrite e in terms of what it actually equals, because remember that e is equal to negative m alpha squared over 2 h bar squared. So this is going to give us m alpha v over h bar squared theta x minus vt minus theta vt minus x minus I over h bar times negative m alpha squared over 2 h bar squared plus mv squared over 2. And evidently, there's a bit of simplification that we can do here, but I'm going to leave that out for now and not focus on that. What's important here is that this expression is still correct. So if we remember that we have to take this red term and multiply it back onto the top, and we recognize that this expression is effectively unchanged, we can write this in a slightly simpler way and say that the derivative of the wave function with respect to time is equal to the wave function itself multiplied by m alpha v over h bar squared times theta x minus vt minus theta vt minus x minus I over h bar negative m alpha squared over 2 h bar squared plus mv squared over 2, and close this entire thing off in a bracket, and we are done with the time derivative. So now we move on to the x position derivatives. Okay, now let's do the derivative with respect to x. So d psi by dx is going to equal, same thing as before, square root m alpha over h bar at the front times, in fact, you know what? I'm just going to take a shortcut here because we've already done this song and dance once. I'm just going to say the psi itself remains unchanged, and then we have a derivative of everything in here. Negative m alpha over h bar squared x minus vt theta x minus vt minus theta vt minus x minus I over h bar times e plus half mv squared times time minus mvx. And we can go over this significantly faster than we did last time, because we've already done all the subtleties of the derivative, and this is really just the same thing but in terms of x instead of t. So at the front we have negative m alpha over h bar squared, and then we're going to be multiplied by dx of x minus vt multiplied by theta x minus vt minus theta vt minus x plus x minus vt times the d by dt theta x minus vt minus theta vt minus x. And then for the second term, the only x term is at the very back here. So this is going to be plus I over h bar mv, I believe. Yeah, because there's no other x dependency. And at this point, it's just a matter of doing this derivative. So negative m alpha over h bar squared. And then the derivative of x minus vt is just going to be 1. So we're multiplying theta of x minus vt minus theta vt minus x. And you know what? I can actually just get rid of this bracket because they're at the front anyway. And then we're adding x minus vt times the derivative of these two expressions, which is going to give me, in this case, the derivative, and you know what? I wrote this wrong. This is supposed to be d by dx. My apologies. The derivative of x minus vt in terms of x just gives 1, so there's no other extra multiplicative factor to attach at the front. It's going to give me a Dirac delta of x minus vt. And then over here, the derivative of vt minus x is actually going to give a negative 1. So this is going to become plus Dirac delta vt minus x plus I over h bar mv. Once again, by the same logic as before, sort of these two terms can combine to become 2 Dirac delta x minus vt. And once again here, everything here cancels out to 0 because of the fact that if x equals vt, then this expression equals 0 and it cancels out. And if x doesn't equal vt, then this expression equals 0 and it cancels everything out. So our final expression is going to be equal to negative m alpha over h bar squared times, let's do it this way, theta x minus vt minus theta vt minus x plus I over h bar times mv. And at this point, once again, we attach it to the front here. So that means that the derivative of psi with respect to x is going to equal psi itself multiplied. Whoops, that's a kind of poorly drawn psi. Let me just reset that. Psi itself multiplied by the negative of m alpha over h bar squared times theta x minus vt minus theta vt minus x plus I mv over h bar. And I cap this off. And with that, we're done with the first derivative. Now we can move on to the second. Okay, now we do the second derivative. So, whoops. d2 psi by dx squared is going to equal, and via product rule, d psi by dx times negative m alpha over h bar squared times theta x minus vt minus theta vt minus x. Whoops, forgot to cap that off. Sorry. Plus I mv over h bar, and then added with psi times d by dx of the same thing, negative m alpha over h bar squared, theta of x. And you know what? Actually, I think I'm going to move this down a line. Added with x minus vt minus theta vt minus x plus I mv over h bar. So let's take this step by step and separate these into two expressions. So I'm going to do this first one in red. I'm going to do the second one in green. So for the red expression, we already have d psi by dx. It's going to give us psi times, in this case, the squared result. So actually, you know, let me make this a little bit better. So the red term is going to give us psi multiplied by everything again. So this is going to be negative m alpha over h bar squared, theta x minus vt minus theta vt minus x plus I mv over h bar squared. And then the green expression is going to give us, let's see, psi multiplied by, so the negative m alpha over h bar squared comes out as normal. And then we have the derivative expression of the interior terms. So this is going to give us a Dirac delta of x minus vt, and then added with a Dirac delta of vt minus x, yeah, because the negative one carries out, and then the imv over h bar doesn't survive. So that gives us, let's see, second derivative of psi with respect to x squared is now equal to psi times negative m alpha over h bar squared theta x minus vt minus theta vt minus x plus imv over h bar squared, and then added with psi times negative m alpha over h bar squared times the Dirac delta x minus vt plus the Dirac delta of vt minus x. And at this point we can distribute out the psi, so this is going to give us psi multiplied by, oh god, the number of brackets I have to put here is starting to get very annoying. Negative m alpha over h bar squared times theta x minus vt minus theta vt minus x plus imv over h bar, cap everything off with a big bracket, square this, and then minus m alpha over h bar squared times Dirac delta x minus vt plus Dirac delta vt minus x. And now I have to distribute out this binomial, which is going to be very annoying. Let's cap off this expression over here. So this is going to give me, let's see, negative m alpha over h bar squared times theta x minus vt minus theta vt minus x squared, and then subtracted by imv over h bar times m alpha over h bar squared times theta x minus vt minus theta vt minus x. And we're doing this twice, so add a 2 at the front, and then finally this final term squared, which is going to be minus m squared v squared over h bar squared. Okay, let's see, what does this give us? This is going to give us at the front, this is going to give us m squared alpha squared h bar fourth times theta x minus vt minus theta vt minus x squared. And then this is going to give us over here, let's see, minus 2i m squared alpha v over h bar cubed, I believe. 2i m squared alpha v over h bar cubed, yeah, multiplied by theta of x minus vt minus theta vt minus x. I keep forgetting to cap off the bracket, my apologies. And then finally, minus m squared v squared over h bar squared. And let's see, at this point, we have to expand this term. So let me see. Right, so we don't actually have to multiply this out the entire way, we can take advantage of knowing what this already equals, because we know that this expression here is a piecewise, which equals, +1 when x is greater than 0 and -1 when x is less than 0. So if we square this, then this is going to become a piecewise that equals 1 when x is greater than 0 and also 1 when x is less than 0. So this is actually just equal to 1 if you square it. So the final resulting expression is just going to be m squared alpha squared over h bar to the 4th minus 2I m squared alpha v over h bar cubed times theta x minus vt minus theta vt minus x minus m squared v squared over h bar squared. And at this point, we can now finally sort of plug everything back in, and what we're going to get is that the second derivative of psi with respect to x is going to equal psi multiplied by m squared alpha squared over h bar to the power of 4th minus 2I m squared alpha v over h bar cubed times theta x minus vt minus theta vt minus x minus m squared v squared over h bar squared. And then we have to attach this thing at the back, so minus m, what is it? M alpha over h bar squared. M alpha over h bar squared, Dirac delta x minus vt, plus, I think, yeah, Dirac delta vt minus x. And then once again, we can take advantage of the fact that Dirac deltas do not care for inverses in their arguments or negatives in their arguments. So this actually equals m squared alpha squared h bar to the 4th minus 2I m squared alpha v over h bar cubed minus m squared v squared h bar squared. Oh, whoops, I forgot to add the internal bracket. This is a very painful expression. Theta x minus vt minus theta vt minus x minus m squared v squared over h bar squared, and then subtracted by 2m alpha h bar squared Dirac delta x minus vt, where once again, I'm taking this expression and I'm recognizing that Dirac delta of x minus vt is actually equivalent to Dirac delta vt minus x. So I'm rewriting it that way. And with that, we're done with the second derivative. We can actually move on to plugging this into the Schrodinger equation. Okay, now comes the final part, which is to verify that the Schrodinger equation is actually equivalent. So let's write everything out. So we have the Schrodinger equation right here. We have v right here. We have e right here. I'm going to write the first left side in red. I'm going to write the right side in green because the resulting equation is pretty long and disgusting looking. So let's start with the left side. So we have I h bar d psi by dt, which is going to equal I h bar times, as we have up here, psi. And actually, we can just get rid of the psi's completely because we know that both sides are going to have exactly a factor of psi at the front distributed out, so we can just get rid of the psi and ignore that altogether. So we have I h bar times m alpha v over h bar squared, I think. M alpha v over h bar squared, yeah. And you know what, let's bracket everything off. Multiplied by theta of x minus vt minus theta vt minus x. There we go. Minus I over h bar times negative m alpha squared over 2 h bar squared plus m v squared over 2. Close everything off. And at this point, we just have to distribute things in. So we have I m alpha v over h bar times theta x minus vt minus theta vt minus x, and then added with im alpha squared over 2h bar cubed minus, or actually, sorry, I just had a bit of a blank right there. I want to multiply the IH bar to the front, so this is going to give me IH bar multiplied by negative I over H bar. The H bars cancel, the two I's make a negative, that becomes a positive. So this is going to give us minus m alpha squared over 2h bar squared plus mv squared over 2. Let me just double check that that is in fact correct. Theta x minus vt minus theta vt minus x minus m alpha squared 2h bar plus mv squared over 2. Yeah. So next we do the green side. So minus h bar squared over 2m times the second derivative, which is going to give us this mess. Remember, once again, we ignore all the psi terms because those just factor out when we're checking the Schrodinger equation. So this is going to be multiplied by this long, painful thing. It's going to be m squared alpha squared over h bar to the fourth minus 2im squared alpha v over h bar cubed times theta x minus vt minus theta vt minus x minus m squared v squared over h bar squared minus 2m alpha over h bar squared times the Dirac delta of x minus vt. Close everything off, and then we're adding the potential, which is going to be minus alpha Dirac delta x minus vt. So at this point, this is going to give us, let's see, negative h bar squared m squared alpha squared over 2m h bar fourth plus 2im squared alpha v h bar squared over 2m h bar cubed times theta x minus vt minus theta vt minus x. I don't know why I even introduced the signum function if I'm not going to use it, but here we are. Plus h bar squared m squared v squared over 2m h bar squared plus 2m alpha h bar squared over 2m h bar squared Dirac delta x minus vt minus alpha Dirac delta x minus vt. So at this point, the h bar squares cancel to make a squared, the m cancels, so we get m alpha squared over 2h bar squared with the negative in front, so negative m alpha squared over 2h bar squared. Let's see, the 2's cancel, the m's cancel, the h bar cubed cancels with the h bar squared, so we have plus I m alpha v over h bar times theta x minus vt minus theta vt minus x. Over here, h bar squares cancel with that, m cancels with the m, so plus mv squared half. Over here, the two m's cancel, the h bar squares cancel. We have plus alpha Dirac delta x minus vt minus alpha Dirac delta x minus vt, so that just cancels out to nothing. And if we look, we have a matching term here with this, we have a matching term here with this, and we have a matching term here with this. So the Schrodinger equation is verified. This is in fact a valid solution, and we are finally done with part A. Okay, part B, we want to find the Hamiltonian expectation value. So to do that, we do the same property that we've been doing all this time, which is that the expectation value of h is going to be equal to the integral from negative infinity to positive infinity of psi star, which is the complex conjugate, with the h hat operator acting on psi. Close this with the dx. And what we have with h hat is going to be the integral from negative infinity to infinity of psi star, and the h hat operator looks like negative h bar squared over 2m times the second partial with respect to x squared minus alpha Dirac delta x minus vt from the potential energy multiplied by psi. And I close this off with a dx. So then at this point, if we plug everything in, this is going to give us, let's see, because we have everything that we've defined here. And this is actually where the signum function is going to become useful, because it sort of condenses down our formula a lot more and actually makes it a lot easier to see what's happening. So we're going to rewrite from now on every instance of the step function appearing as signum, in which case this is going to give us the integral from negative infinity to infinity of psi star multiplied by negative h bar squared over 2m times the second derivative, which is going to give us psi multiplied by everything here. So in fact, it might be actually better to cap this off with a curly bracket. So psi, and then multiplied by m squared alpha squared over h bar to the power of fourth minus 2im squared alpha v divided by h bar cubed times signum of x minus vt minus m squared v squared over h bar squared minus 2m alpha over h bar squared Dirac delta x minus vt. And actually, I think, you know what, just to make this a little bit simpler, I'm going to take this out of my bracket preemptively and just multiply by h bar squared over 2m. So the h bar squared at the bottom disappears, the 2m at the top disappears. It's just giving us minus alpha Dirac delta x minus vt. And then this is going to be subtracted by, let me just double check that this is actually, yes, this negative becomes a positive, and then we're subtracting by alpha Dirac delta x minus vt, and instead of having the psi here, I'm just going to pull the psi out of everything. Like this. So in that case, the psi's will combine to get magnitude psi squared multiplied by, these two evidently go to 0. So we have now negative h bar squared over 2m times m squared alpha squared h bar fourth minus 2im squared alpha v h bar cubed signum x minus vt minus m squared v squared h bar squared. Close this with a dx, and over here I also need to close this with a dx. So at this point we can split this. So this is going to be, I'm going to factor out the negative h bar squared over 2m. And then at this point what we have is going to be actually two different integrals. In order to sort of make this a little bit easier, I'm going to write this as, let's see, I'm going to start this as two separate integrals. An integral from negative infinity to infinity of magnitude psi squared times negative 2im squared alpha v over h bar cubed signum x minus vt dx. And then we're adding with an integral from negative infinity to infinity of magnitude psi squared. This is going to give m squared alpha squared h bar fourth minus m squared v squared h bar squared. Closing this with the dx. So what I've done is I've isolated the signum into its own integral, and I've taken the normal stuff on the other two terms and put them into their own integral. So at this point, I can recognize that this is pretty much just, you know, a constant. You know, there's no x term, so I can just pull it straight out. Same thing over here. So I'm going to get negative h bar squared over 2m multiplied by negative 2im squared alpha v over h bar cubed times the integral from negative infinity to infinity of magnitude psi squared signum x minus vt dx minus h bar squared over 2m times m squared alpha squared h bar fourth minus m squared v squared over h bar squared. integral from negative infinity to infinity of magnitude psi squared dx. Now, let's cancel some stuff. So the positives here, the two negatives cancel out positive, h bar squared cancels out h bar cubed. 2m cancels out with a 2 and cancels out with an m, so we're left with im alpha v, I believe. Yeah, over h bar times the integral from negative infinity to infinity, mag psi squared times signum x minus vt times dx. And then this is going to be subtracted by, let's see, h bar squared cancels out with this, makes a squared, cancels out with h bar squared completely over here. The m cancels out with the m here, cancels out with the m here, so we're left with minus, so I'm gonna switch this around. So I'm gonna get plus, and then mv squared over 2 minus m alpha squared over 2 h bar squared. And this is the integral from negative infinity to infinity of mag psi squared dx. So we're seeing mag psi squared dx a lot. Let's actually verify what the magnitude of psi squared actually is. So if we look up here, immediately what you should see is that there's a exponential of an imaginary number over here. So when you take the magnitude squared of psi, this exponential just goes to nothing. So we're just left with this term, which we're taking the square of. So this is going to give us m alpha over h bar squared e to the, and we're just going to add a 2 in the exponent. So this is going to give a negative 2m alpha magnitude x minus vt divided by h bar squared. So I'm going to take this, I'm going to move it down. I'm going to say that, okay, if the magnitude is equal to this, then I'm going to get that the expectation value of h is going to be im alpha v divided by h bar, integral from negative infinity to infinity, m alpha over h bar squared, signum x minus vt, e to the negative 2m alpha magnitude x minus vt over h bar squared. This is in dx. And then we're adding mv squared half minus m alpha squared over 2 h bar squared times the integral from negative infinity to infinity, m alpha over h bar squared, e to the negative 2m alpha magnitude x minus vt, excuse me, all divided by h bar squared, close off with the dx. And at this point, we're going to do what we always would do in a situation like this, where we have exponentials of some function of x, and we're trying to integrate with respect to dx, and that's where we're going to do u sub to simplify things a little bit. So if we do u sub, then we can say, okay, suppose that u is equal to x minus vt, and I want to substitute everything in this into u, in which case, since we're deriving with respect to x, then du by dx is going to equal dx, because v and t aren't part of the x variable, in which case this is just a direct substitution. So in that case, the expectation value of h is now going to equal, let's see, I m squared alpha squared v over h bar cubed, because I'm pulling out the factor at the front, times the integral from negative infinity to infinity, signum of u times e to the negative 2m magnitude u. So you know what, let's write this out a little bit. Negative 2m alpha over h bar squared times magnitude u. And we're closing this with a dx, and then we're adding m alpha over h bar squared times mv squared half minus m alpha squared over 2 h bar squared, integral from negative infinity to infinity, e to the negative 2m alpha over h bar squared magnitude u du. And at this point, the signum is, this is where signum becomes a very useful thing to have, because it makes everything a little bit nicer and condensed. Because remember, signum of u is basically just an argument that says that it equals 1 when u is greater than 0 and negative 1 when u is less than 0. And if we see here, we have an exponential of an absolute value of a variable. So what this means is that when x is positive, this exponential is e to the negative 2m alpha u over h bar squared. And when u is negative, it's equal to e to the positive 2m alpha u over h bar squared, where u is going to be negative. So no matter which direction we go from the origin, it's always going to be an exponential decay. If you were to graph this out, this is effectively a Gaussian. It looks something like that. Not quite a Gaussian, my apologies, but something akin to this. It looks something like this. So what we're doing is that, not quite a Gaussian. My apologies. I used the wrong vocabulary there, but it's basically it's an exponential decay on both sides, going from some positive value, whatever this positive value is. And the thing about the signum function is that what it's going to do is it's going to reflect, because remember, an integral is the sum of the area underneath, or the integral is the area underneath a curve. So what the signum is doing is it's going to basically reflect everything on the negative side upside down. So what'll happen is that you have a positive, the part of the integral that's positive going from 0 to infinity, and you have a part of the integral that's negative going from negative infinity to 0. And since these both of these functions are effectively sort of even initially, because of the fact that this exponential was initially an even function, what's going to happen now is that if we reflect it, this just becomes an odd function, in which case this is a symmetric integral of an odd function, which just means that this entire term is just going to equal 0. So we're just left with this second term over here. So the expectation value of the Hamiltonian, aka the expectation value of the energy, is actually equal to m alpha h bar squared mv squared over 2 minus m alpha squared over 2 h bar squared. And at this point, we can split this integral into two. So we're going to get an integral from negative infinity to 0 of e to the positive 2m alpha over h bar squared times u. Because remember, u now is going to be negative here, and we're doing this with du. And then we're adding an integral from 0 to infinity of e to the negative 2m alpha over h bar squared times u du. Evaluating this integral, this is going to give us, let's see, e to the 2m alpha over h bar squared times u multiplied by h bar squared over 2m alpha. Is that correct? Yeah. Evaluated from negative infinity to 0 plus e to the negative 2m alpha over h bar squared times u multiplied by h bar squared over 2m alpha, going from 0 to infinity. In which case, at this point, this is going to give us, let's see, h bar squared over 2m alpha times 1 plus 0. And we're adding h bar squared over 2m alpha times, at infinity, this is 0. And then at 0, this is going to be 1. So at this point, we just have h bar squared over m alpha, and I need to extend this really quick, so give me 1 second. There we go. So then, if we plug this back into the expectation value, this is going to equal m alpha over h bar squared times mv squared over 2 minus m alpha squared over 2 h bar squared multiplied by h bar squared over m alpha. Just make sure that's correct. Yeah. In which case, these two terms cancel out to 1. What we're left with is negative m alpha squared over 2 h bar squared plus 1/2 mv squared. Now, finally, we're asked to comment on the significance of this. And if you go back to 2.5, you will see that the energy of the traditional delta well, where if we have something that looks like this, where we have a delta function is equal to negative, alpha direct delta of x, when you have a well like this, the corresponding associated energy of that well, there's only a single level, is equal to negative m alpha squared over 2h bar squared. So this term here is evidently just the energy of the standard well, and then what happens here is we have an extra 1/2 mv squared term that's associated with the well moving. Because remember, at the very start of this, what we're dealing with is a moving delta function well. So this energy is exactly what we would expect. The energy of a moving delta function well is evidently just the standard energy of a delta function well with this additional 1/2 mv squared that comes from the fact that the delta well is now moving, and therefore the particle in the well of mass m is now moving with velocity v. So because of that, it now has this associated kinetic energy associated with it, and it's very nice that we get this result because sort of it's exactly what we would expect according to sort of classical mechanics, in that as we have something that's not moving and it starts moving, it gets an associated kinetic energy of 1/2 mv squared. So that's very nice, and sort of insinuates that we have done this problem correctly. And with that, we are complete. We have completed 2.50. Okay, apologies. I was looking at this post-recording and realized I made a bit of a mathematical mistake here. This integral, let me just do this in red. So this term over here, which corresponds to here, this, when you take the integral of this, this is supposed to be a negative. So this is supposed to be a negative, and when you do this actual integrand, there's going to be a negative that shows up here. So the two negatives cancel out to make the positive. At the end, it's the same thing, but it was just a bit of a arithmetic error here that caused me to sort of skip a step over here. So because of that, I hope that didn't cause too much confusion. Overall, a very minor error, but because of that, I didn't feel like re-recording the entire thing just to fix this thing. So I'm editing it, or not editing, but just adding to this after the tutorial, just sort of to explain myself here.